Alright, hello and welcome to our presentation about antibiotic contamination of water. First, let me briefly introduce antibiotics. Antibiotics are compounds which are used to treat bacterial infections, and they do so by either killing or inhibiting the growth of the infection by binding to one of its reproductory proteins of the bacteria. Here we have some examples of antibiotic family. We have penicillins, cephalosporins, carbamazepines, and monobactams. Uh, this is the active part of the antibiotic. We can attach like different R groups to make it bind to the target site as we need. They are very effective. After discovery of penicillin, its consumption raised rapidly, and subsequently so did the antibiotic resistance. So because of how popular and abundant use they became, bacteria starts to evolve defense mechanisms to withstand their effects. It can do so by we have two strategies to do so. It can either stop the antibiotic from reaching the target at a high enough concentration, or it can modify the antibiotic's target so it can no longer do its job effectively. And here we have some mechanisms. First one is a pump. So pumps in the cell wall of the bacteria, transport radioactive compounds through the cell, out and in, and it can modify itself so it's gonna just flush out the antibiotic out of itself. The membrane itself can be also modified so it doesn't allow the diffusion of the antibiotic into the bacteria. Uh, it can also uh, evolve and produce enzymes which destroy the antibiotic itself. An example would be beta-lactamase, which destroys the beta-lactate ring of the penicillin family group by breaking this carbon-nitrogen bond and oxidizing this carbon. It can also modify the target, which means it can either change the protein structure of the target molecule, so it has a different structural component, structural conformation, so the antibiotic can no longer bind to it as well, or it can just like add like a group, just camouflage it or protect it in any way. The highest concentration of the antibiotic contamination is in places where we use them the most. Good example of this are of course hospitals, because that's where we can find the infected patients, which we treat with the antibiotic. A big producing factor of contamination are also is also general populace, since it's largely unmonitored and anybody can buy them and take them, and since 70% of the antibiotic just passes through us and goes to the sewage into water treatment facilities, which is another huge cesspool of of antibiotic contamination, therefore antibiotic resistant bacteria, which then just which water treatments don't really treat water. They don't really eliminate the antibiotics in them, so they just get passed back into the environment. One of the biggest factor in the contamination is like animal agriculture, aquaculture, and the animals. Over 80% of our whole production of antibiotics goes here, and it's used like rather like wastefully. You just like sort of throw it at animals like in an attempt to like prevent the disease rather than like applying it, because it's much easier to do that. And also industry plants are a big contaminated too. They release their sewage into the water and back into the environment. Uh, yeah, and most of these, for example, the industries can be resolved by stricter policing, But lots of these issues can also be tackled like individually. For example, if you become vegetarian, you reduce the impact the animal agriculture is gonna have, or you can avoid like self-administering antibiotics. All right, here are references, and I hope you enjoyed my part, and I'll hope you also enjoy Steven's part, which is coming next.
Thank you, Jerry. Before we move on, let me introduce you three antibiotics which I found is the most common one in ocean, river, and underground system. Tetracycline is an antibiotic used to treat a number of infections. This includes cholera, brucellosis, plague, malaria, and syphilis. It's taken by mouth, and common side effects include vomiting, diarrhea, rash, and loss of appetite. Azithromycin is an antibiotic medication used for treatment of a number of bacterial infections. This includes middle ear infection, strep throat, diarrhea, and certain other intestinal infections. The last one is an antibiotic treat for bacterial infection as well, and the most known one is the urinary tract infections. It is effective against both gram-positive and gram-negative bacteria, such as E. coli. It can be seen from the above picture that antibiotics has been detected in oceans, rivers, lakes, groundwater, and other water bodies in many regions of the world. It can be seen that antibiotic pollutants are universal in pollution of natural water bodies, and by summarizing the published literature, the article summarizes the main way antibiotics enter the natural water bodies, including sewage treatment plants, farming, livestock farms, and improper disposal of medicine. Only a part of antibiotics can be metabolized in organisms. According to a published literature, 10% to 9% of antibiotics are excreted from urine and feces in the forms of maternal structure and then enter the sewage treatment plant. However, the biological wastewater treatment process currently used in most areas cannot effectively remove antibiotics in wastewater because most of the antibiotics have poor biodegradability. The removal rate of antibiotics in sewage treatment plants is related to their physical and chemical properties. But the removal effect of most antibiotics is not ideal, which causes them to enter the sea or river with effluent. It can be seen that the effluent of the sewage treatment is one of the most important sources of antibiotics in natural water environment. This is the data I collected from the published literature. The ocean is the most important part of natural water on Earth, and there are many kinds of organisms in the ocean. The ecosystem is extremely large, so the pollution of the ocean by antibiotics pollutants cannot be ignored. Many studies have investigated the contamination of antibiotics in some sea areas at home and abroad. Rivers are an important part of the Earth's freshwater resources and are one of the main sources of water for human activities, such as industrial water and drinking water. Its water quality not only affects the organisms in river ecosystem, but also directly affects the industrial and architectural production, and most importantly, human health. The pollution of river by antibiotic pollutants is also related to the health of the river ecosystem, so it has aroused widespread concerns. As shown in this table, according to existing literature reports, a variety of antibiotics has been detected in many rivers at home and abroad, with concentration ranging from 0.13 to 1,900. Antibiotic pollutants have been detected in many important rivers in our country. Both lakes and groundwater are important freshwater resources on Earth. From the literature involved and comparing those with the ocean and river antibiotics, the concentration of antibiotics in lakes and groundwater is much lower than that in river and ocean. This may be due to the fact that human activities are more frequent in ocean and river than in other water bodies. But the question is, how do we obtain those data? There are many analytical techniques we can use, and the one I'm going to mention today is HPLC. High Performance Liquid Chromatography, HPLC, formerly referred to as high pressure liquid chromatography. It's a technique in analytical chemistry used to separate, identify, and quantify each component in a mixture. It relies on pump to pass a pressurized liquid solvent containing the sample mixture through a column filled with a solid absorbent material. High-performance liquid chromatography is basically a highly improved form of chromatography. Instead of a solvent being allowed to drip through a column under gravity, it is forced through under high pressure of up to 400 atmospheres. That makes it much faster. It allows you to see a very much smaller particle size for the column packing material, which gives a much greater surface area for interactions between the stationary phase and the molecule flowing past it. This allows a much better separation of the components of the mixture. And the other major improvement over column chromatography concerns the detection methods which can be used. These methods are highly sensitive. Because of the pressure involved, it is not the same as in gas chromatography. The time taken for a particular compound to travel through a column to the detector is known as the retention time. This time is measured from the time at which the sample is injected to the point at which the display shows a maximum peak for that compound. Different compounds have different retention time. For a particular compound, the retention time will be varied depending on the pressure used, the nature of the stationary phase, the exact composition of the compound, and the temperature of the column. That means that the condition has to be carefully controlled if we are using retention time as a way of identifying compounds. There are also several ways of detecting when a substance has passed through the column. A common method which is easily to be explained is using the UV absorption. Many organic compounds absorb UV light of various wavelengths. If you have a beam of UV light shining through the stream of liquid coming out of the column, and a UV detector on the opposite side of the stream, you can get a direct reading of how much of the light is absorbed. The amount of light absorbed will depend on the amount of a particular compound that is passing through a beam at a time. You can also use the peaks as a way of measuring the quantities of the compound presented. Let's suppose that you are interested in a particular compound X. If you injected a solution containing a known amount of pure X into the machine, not only could you record its retention time, but you could also relate the amount of X of the peak that was formed. The area under the peak is proportional to the amount of X which has passed the detector, and this area can be calculated automatically by the computer linked to the display. The area it would measure is shown in green in the diagram. If the solution of X was less concentrated, the area under the peak would be less, although the retention time would still be the same. This means that it is possible to calibrate the machine so that it can be used to find how much of the substance is presented, even in very small quantities. In the diagram, the area under the peak for Y is less than that for X. That may be because there is less Y than X, but it could equally well be because Y absorbs UV light at the wavelengths you are using less than X does. There might be a large quantity of Y presented, but if it only absorbed it weakly, it would only give a small peak. Although the concentration of antibiotics in the natural water environment is relatively low, the potential harm to the ecosystem and human health cannot be ignored. As antibiotics are frequently detected in natural water environment, there are more and more studies on their hazards. According to the existing literature report, the harm of antibiotics in the natural water environment can be attributed to three aspects, namely biological toxicity, induction of drug-resistant bacteria or drug-resistant genes, and most importantly, the threats to the safety of drinking water. Antibiotic pollutants may threaten the safety of drinking water. Drinking water source may be contaminated by antibiotics. If the river purification plant cannot remove the antibiotics, it will enter the drinking water pipe network. As I mentioned for the previous page, sulfamethoxazole is the most common antibiotics found in river. And the study has shown that the influent water of 17 water purification plants containing that antibiotics has the highest concentration of 110 ng per liter. The influence of 11 water plants containing another commonly seen antibiotics, the highest concentration is 11 ng per liter. Regulation of sludge application, protection of drinking water catchment areas, and soil management will all be the solution to avoid or reduce the contamination of the environment by antibiotic resistance. And more studies can be found on the graph I provided above. This will be the end of our presentations. Jerry and I have covered the water contamination by the antibiotics. We have also introduced you two analytical techniques. I hope to see you soon and have a nice day. Thank you for watching.